would like to thank the organizers of this conference, and especially Laurent de Cresson and Frédéric Chazal for inviting me in that session. Before starting, a small advertisement. We have a research group at the CNRS called GeoSto, a research group on stochastic geometry. It started in 2012 and has just been renewed for 4 more years. And it is open to anyone interested in geometric probability and spatial statistics. And I think we are now about 130 members, and including all the previous speakers of that session. Okay, so my talk is designed as a small survey on the topic of random polytopes, and especially I will deal with some of the results contained in 4 papers. The first one I co-wrote it with Joe Jukic and Thomas Schreiber, and the 3 last ones were co-written with Joe Jukic. So I will introduce the models of random polytopes I will consider in this talk. I will discuss a little bit the existing literature, then I will provide my main results, which will deal with variance asymptotics and the explicit calculations of variances of some functionals connected to the random polytopes I will define. And I will give a sketch of proof for one of the model I will introduce, which is called the Gaussian polytope. Okay, so what is a random polytope? I have a first model called uniform polytope. Consider a convex body of the Euclidean space of dimension d, Rd. So this convex body has a non-empty interior and has finite volume. Then take a sequence of random variables which are independent and uniformly distributed in your mother body K, and then construct the convex hull of n of these points. And you are interested in the asymptotic behavior of this convex hull when the size of the input n goes to infinity. So you can see here on the picture simulations in the unit ball and in the square. You can see, of course, then the more you throw points inside your mother body, the closer the convex hull is to the initial convex body. This topic of random polytope was introduced more than 150 years ago in 1864 by Sylvester in the Educational Times. He asked, what is the probability that taking 4 random points, you will get a foregone? That is, that all these 4 points will be the vertices of a quadrilateral. And then the theory has been developed since around 1950 because it has connections with several fields. First with convex geometry, because you can see these convex hulls are as approximation of your mother body. So this is sort of a polytopal approximation of a convex body, which can be smooth or polytopal itself. Also, it has connection with computational geometry, because, for instance, the number of extreme points that you will get for this random polytope will give you information on the complexity of an algorithm for constructing a convex hull. There is also connection with statistics via the model of convex hull peeling when we have to deal with multivariate data. And so because of all these potential applications, the theory of random polytopes has been developed for now more than 50 years. Okay, I will need to extend my model that I call a binomial model of a uniform polytope. It was called binomial because if you take n points inside a convex body, then if I consider a small part of this convex body, the number of points falling into that small part is binomial distributed. But if now you consider a Poisson number of points inside your convex body, then the number of points which will fall inside a part of your convex body will be also Poisson distributed. Okay? And as a matter of fact, it will be easier to deal with this Poisson model of a random polytope in the rest of the talk. It will be easier to prove limit theorems as law of large number of central limit theorems, and also to calculate expectation and variances. So from now on, my input will be a Poisson point process which is homogeneous of intensity measure lambda gx. So lambda is the mean number of points per unit volume. And then you consider the convex hull of all the points which fall inside your convex body, your mother body K. And so you are interested in describing some of the functionals connected to this random polytope when lambda goes to infinity, sorry. My second model is called the Gaussian polytope. The only difference will be that you will consider Gaussian points instead of a homogeneous Poisson point process. That is, okay, either you get the binomial model by taking a fixed number of independent and uniform and identically distributed points with a distribution which is Gaussian with this density, and you construct the convex hull, or you take a Poisson point process of intensity measure proportional to the Gaussian density. And you ask for the behavior of that convex hull when the coefficient lambda here in front of the Gaussian density goes to infinity. So here are a simulation of the Gaussian polytope. It seems that the more you throw points, the closer the convex hull is to a ball. It seems that there is asymptotically a spherical shape due to the invariance by any rotation of the Gaussian distribution. And indeed, there was a result due to Geoffroy in 1961, which shows that almost surely the Hausdorff distance between the convex hull of n points and n points distributed with the Gaussian distribution, and the ball centered at the origin and of radius square root of 2 log n goes to 0 when n goes to infinity. So I will use the fact that I have a critical radius and that almost all of the extreme points should be near to this sphere of radius square root of 2 log n. Okay, so now it is time to discuss the functionals that I will deal with in the rest of the talk. And there are, first, the number of k-dimensional faces. For instance, if k is equal to 0, then I get the number of extreme points. If I take k equal to d minus 1, I will get number of facets of my random polytope. And of course, I am interested with the volume or the defect volume. So for instance, the volume of the complementary set of the convex hull inside the mother body. And there is an important relation between the mean number of extreme points and the mean volume or the mean defect volume of a random polytope in the uniform case. Indeed, you can write the mean number of extreme points as n when you throw n points times something which is of course smaller than 1, and it is equal to 1 minus the probability that if I have already thrown n minus 1 points, the nth point will be inside the convex hull of the first n minus 1 points. So the probability is computed like this because this is a uniform distribution. And so this point will be extreme if and only if it is not inside the convex hull of the n minus 1 first point, sorry. Okay, so there are results due to many people. A seminal work is due to Reni and Zulanke in 1963. And in that work, there was already an explicit computation of the expectation of extreme points and the expectation of the mean area, the expectation of the area in the planar case for a uniform polytope. And it has been extended since then by many people, including Rolf Schneider, Affentronger, Viarca. And the result is the following. The mean number of extreme points, or the mean number of k-dimensional faces, grows like lambda to the g minus 1 over g plus 1. So it has a polynomial growth, which is independent of k, the order of the faces that you consider, save for the fact that the constant in front of it is explicit and depends on both d and k. And here, the dependency on the mother body, the convex body k, is given by this integral, which is the integral of the Gaussian curvature to the 1 over g plus 1 along the boundary. So not very intuitive, but that is the dependency on k of this mean number of extreme points when the size goes to infinity. The size of the input goes to infinity. In the case of a polytope, this is completely different. And the reason is the following. Maybe, do I have a chalk anywhere? Okay. If you think of the square, and if you throw your points inside the square, you can see that you need less extreme points to approximate the square, because along an edge of the square, you need only an edge, almost only an edge of your convex hull to approximate the square. But most of the extreme points will be very near a vertex of the square, because you need to turn. So most of the extreme points will be in the vicinity of the vertices of your polytope, but still the growth of the number of extreme points will be much slower than the growth in the case where the boundary of k is smooth, and indeed it will grow logarithmically fast. So the growth is logarithmic, and the dependency on k, when k is a polytope, is constant times the number of flags. And number of flags, what is it? A flag is a sequence of a 0 face, 1 face, 2 face, a 3-dimensional face, etc., which are included. So you take, for instance, in dimension 3, this, if I take this vertex, this edge, and these 2 faces, this is a flag of the cube. Okay, and in the case of Gaussian polytope, well, the growth is also logarithmic. And why is it logarithmic? This is because, maybe I need to go back to the picture. You can understand this fact on this picture. Most of the points will be very near the origin, and very few of the points, because of the distribution tail of the Gaussian distribution, few points will be extreme, and few points means their number will grow logarithmically fast. Okay. Now I will present the main results of our work, which are explicit computations of variances. So all the results I presented on expectations were obtained in the 20th century, but from 2000 on, people started to work on central limit theorems and getting variance estimates. But to the best of my knowledge, no one was able to prove that there was a variance, a limiting variance for each of these functionals. We had only lower and upper bounds. And so the main goal of our work was to get these limiting variances. So here are our results. First, I consider the uniform model. So I have a mother body. I throw inside this mother body either n points or a Poisson number of points. Here it is written for a Poisson number of points. And I assume that the boundary of this mother body is smooth. And when I say smooth, it means with a C3 boundary. And I can show that the variance is, it is proportional asymptotically to lambda to the d minus 1 or d plus 1, so the same as the expectation, which has to be expected because it is the same as when you consider the sum of a large number of IID random variables. The variance has the same growth order as the expectation. And the dependency, well, we have an explicit limit, and the dependency on k is exactly the same as for the expectation. This is this strange integral, which is called the affine area of k. And same for the volume. And the best result before ours was due to Matthias Reitzner in 2005, and it was only a lower and upper bound of the variance. Okay, in the case of a polytope, still in the uniform model, we can show that we have a limiting variance. The only problem is that we cannot show it for just any polytope. We have to deal with a simple polytope. And what is a simple polytope? It is a polytope such that each of the vertices is up to an affine transformation like this. It means that it is included in exactly d facets, that is d minus 1 dimensional faces of the mother body. And in that case, we can show that the variance behaves like log to the d minus 1 lambda times a constant, something which depends only on the dimension and k, times f node of k, which is exactly the number of vertices of the mother body. And this can be explained in the following way. You have a contribution of each of the vertices. I told you before, most of the extreme points will be near the vertices of your square in dimension 2. So you have a contribution near each of the vertices, but the problem is you have to show that these contributions decorrelate when the size of the input goes to infinity. And it is far from being obvious. I mean, it was easier to do it for the expectation because it was obviously additive. But here for the variance, you need to show that it decorrelates. And it implies that you need to show that with high probability, you have indeed independency between what happens in the vicinity of this vertex and what happens in the vicinity of another vertex. Okay, and the best result before that was due to Barani and Reitzner in 2010. And it was also a theta of log to the d minus 1 lambda. And lastly, same kind of results for the Gaussian model. We have, how much time do I have, Frédéric? 1 minute. Okay. I will go faster, I believe. Okay, so we have the same kind of results for the Gaussian model. So I still have one section, but will be very fast, I'm sure. So maybe it is better that I explain the method for proving this kind of variance asymptotics only with expectation. I know it is disappointing, but if we can understand this for the expectation, it will be already a big step. The idea is that any of the functionals that I consider can be written as the sum of scores, and these scores are random variables which depend on both one point and the Poisson point process. And this score, for instance, can be, if I compute the number of extreme points, it would be 1 if one point is extreme and 0 if not. And you sum all these scores, and the hope is that these scores will be, they are not independent. That's the main problem. But they are more or less independent if you look at scores of points which are far enough. Okay, and we use Maker-Slavniak formula to show that this expectation can be written as an integral, and then you have to compute the asymptotics for the expectation of the score. And you do the same for the variance, and I think my time is over. So, okay, thank you very much for your attention.
So the fact that you look for affine invariant quantity can help?
Of course. Of course. I didn't say it, but we do it for mother body with volume 1 to start with. And to deal with the uniform model inside polytopes, you need all the time to apply affine transformations so that you will be in the corner of a cube. And then you can work in the corner of a cube. So you use it all the time, really.
A quick question about the result you get. You don't have any result about the rate of convergence. The idea is that you have this difference between the smooth and polytope case.
Yes.
And in some sense, if you take a smooth convex body, you can approximate.
I know. I thought of that.
In some sense. And you get.
I see your point. I see your point.
Something interesting in the
I'd like to do the same. We were unable to do it up to now. But indeed, you would think that taking the limit from the smooth case to the polytope case would be enough. And right now, I'm unable to do it. But
okay. Thank you again.
thank you.